Yes. All right, welcome to Math466, Lecture 12, Advanced Applied Analysis. There were some technical issues with the lighting, but we have now restored it. Unfortunately, that meant that since the camera had adjusted to no light, it became this massive, you're dying, stay away from the light, so we are resetting the lecture to 0. Fortunately, we had not covered too much. So the idea is to prove the following theorem. As the variance goes to infinity, a normal with mean 0 variance sigma squared modulo 1 converges to the uniform distribution. We showed how to do this using Poisson summation, Fourier analysis. There's a lot of great stuff there. It motivated the need to understand the stuff. It motivated the need to learn complex analysis, to find better ways of finding Fourier transforms, but the proof was involved. So what I want to show now is a proof that I came up with after I wrote the book, which I think is a little bit nicer, and it uses facts of the Gaussian. So we talked a little bit about Chebyshev's inequality. Chebyshev's inequality sucks in some sense relative to the central limit theorem, but the reason it's so bad is because it must apply to all probability distributions with mean 0 and finite variance. If we know we have something like the normal, we could do much better. And we showed how to bound the probability of a normal being far away from its mean. And by far away, we mean relative to the standard deviation. So what I've drawn here is my view of what normals look like with increasing variance. And you can see as the variance gets larger and larger and larger, the normal becomes more and more spread out. And so it's really looking like uniform on small blocks. So if you imagine that the variance is of size 10 to the 1,000, those little things are going to be blocks of size 1. And on blocks of size 1, you really can't see the variation in this. And so what we want to do is, if we want to show that it's uniform, we want to show that the probability that we take a value between A and B mod 1, well, we would take a value between A and B, 1 plus A, 1 plus B, 2 plus A, 2 plus B, 3 plus A, 3 plus B, and just sum them all together. And the idea is, well, since each one of these is approximately uniform, when we sum them all, it should be approximately uniform. The challenge with that, of course, is, well, maybe it's always a little bit larger in the beginning of the interval, and because we're summing it infinitely often, it accumulates. And so maybe it's not going to be uniform. But because the normal is, in some sense, rapidly decaying, maybe everything is okay. So this is the general idea. We're going to now try to make this rigorous. So what I'll do is the following. I'm going to just focus on half of the normal. We'll just focus on x greater than or equal to 0. Do you all agree that if we can do x greater than or equal to 0, then x less than or equal to 0 follows analogously? Good. All right. So now, here's 0, here's 1, here's AB. Here's 2, here's 1 plus A, 1 plus B. So there's a lot of ways to do this. What I'm going to do is, instead of doing a generic A and B, what I will do is I will choose very specific ones. So here's 0, here's 1, here's 1 over n, and here's n minus 1 over n. And here is 2, here's 1 plus 1 over n, and here's 2 minus 1 over n. And we're going to keep marching down like this. If you look at the normal is strictly decreasing as we increase x. So if I look at the probability I'm between 0 and 1 mod n, that's going to clearly beat this probability. And this is going to beat this probability. So the probability that x mod 1 is in 0, 1 over n is going to be strictly greater than or equal to the probability x mod 1 is in n minus 1 over n to 1. Do we all agree on that? Because this beats this because the probability is decreasing. This beats this because the probability is decreasing. Okay? If you want to write it explicitly, this is the sum, and goes from 0 to infinity, of the probability x is in, oh, I shouldn't use n, I'll use m. m plus 1 over n. And this over here would be the sum, m goes from 0 to infinity, of the probability that x is in m minus 1 over n m. Or I guess I want to do m plus 1. M plus 1 minus 1 over n, m plus 1. So just to write it really explicitly. And the reason this is true is because each one of these blocks beats each one of these blocks. Okay? Now here's the trick. This probability we all agree is greater than this probability. But this probability here from 1 minus 1 over n to 1 is greater than the probability from 1 to 1 plus 1 over n. And then the probability from 2 minus 1 over n to 2 is greater than the probability from 2 to 2 plus 1 over n. So really, this stuff over here almost beats this. If I just add the probability from 0 to 1 over n, then I would win, and I can just do comparisons. Because this beats this beats the next one, this beats the next one, and this is just left over. So if I add this probability, then it will beat this. So this is greater than or equal to the probability that x mod 1 is in 0, 1 over n, minus the probability that x is in 0, 1 over n. All I had to do was subtract off that one extra block. So another way of looking at it is, we had A0 beats B0, A1 beats B1, A2 beats B2. And if we add all the A's, it beats all the B's. But we know B0 beats A1, and B1 beats A2, and B2 beats A3. So if we add up all the B's, it beats all the A's minus A0. So we get the sum of the B's is greater than the sum of the A's minus A0. So is everybody comfortable with this argument? What can you tell me about this probability? What's the probability that x is between 0 and 1 over n? I need a sorry, battling a cold. I need a bound for this probability. It's clearly at most 1, it's probability, but that's a useless bound. I want to show that this is small. How small do you think this is? How would I calculate the probability x is in 0, 1 over n? So how would we find that probability? Yeah, probability x is in 0, 1 over n is just the integral from 0 to 1 over n, 1 over square root of 2 pi sigma squared e to the negative x squared over 2 sigma squared dx. X is really, really small, and sigma is really, really large. What can you tell me about this quantity e to the negative x squared over 2 sigma squared? About how large is that? So how large do you think this exponential is? Or if you want, how large is the argument of the exponential? If x is really small and sigma is really large, I have basically e to the what? I have basically e to the 0. So this is essentially 1, and we know, in fact, it's less than or equal to 1. All right, we have a square root of 1 over 2 pi sigma squared, so this is going to be less than or equal to 1 over square root of 2 pi sigma squared times 1 over n. So as sigma goes to infinity, this goes to 0 very rapidly with sigma, no matter what the fixed n is. So what does this mean? Well, if we go back, let's try to get the camera so it'll come back with us. So if we go back over here, nope, do it the old-fashioned way. All right. So if we come back, this probability that we are in 0, 1 over n, if it was uniformly distributed, what should this probability be? It should be 1 over n. It's equal to the probability that when the interval 1 minus 1 over n1 minus a term that's at most 1 over square root of 2 pi sigma squared times 1 over n. So as sigma goes to infinity, this probability and this probability converge to the same thing. What's the only thing they can converge to? 1 over n. Because there's nothing special about going n minus 1 over n. I could have done 0, 1 over n, 1 over n, 2 over n, 2 over n, 3 over n, 3 over n, 4 over n. For all of these things, they all have to go to the same. So what we've just shown is that the interval 0, 1 over n, as sigma goes to infinity, goes to probability 1 over n. This is not the same as doing generic a and b. So what you can do is you give me an a and a b, and what I'll do is I'll choose an n so large that if I take enough of them, it's essentially b. And then I take enough of them so it's essentially a, and I subtract. So I'll leave it as an exercise to pass from this. If you want, you can assume a is equal to alpha over n, b is beta over n for some really large n. And then that will be extremely accurate, and then you'll just sum them and take the difference. So this shows that it does converge to being uniform. I actually like this proof a little bit more than the Poisson, in that you see what's going on and you see where the uniformity is coming from. Notice that it was crucial that our density is strictly decreasing. If the density wasn't strictly decreasing, we couldn't do this argument because we had this whole this beats this, this beats this, this beats this, but this also beats that, and that also beats that, and marching down like that. And it all came down to really, this almost beats this if it wasn't for that damn A0. But because A0 is so small, it doesn't really matter, and in the limit they'll have the same probabilities. So this becomes another way of proving a theorem, and this is one of the big ways of showing that something converges to Benford behavior. You show that its logarithm becomes uniformly distributed. How do you show its logarithm becomes uniformly distributed? Well, if its logarithm happens to become normally distributed with growing variance, then the logarithm mod 1 will be uniform. Okay, any questions on this? Okay, so what I want to do now is I want to do the Fibonacci example, and then I'll use this to motivate a theorem in Fourier analysis that we need. If Professor Silva were teaching the class, he would say a theorem in ergodic theory. So you can prove this theorem in several different ways. Out of curiosity, has anybody taken ergodic theory? Okay, good. Well, okay, it's not good that you haven't taken ergodic theory, but it means I have first dibs on showing you how to look at this theorem. So claim, or theorem. Fibonacci's are Benford. And so it doesn't really matter, but we'll define, fn plus 1 is fn plus fn minus 1. f0 is 0. f1 is 1. All right. Has everybody seen how to find Benet's formula for the Fibonacci numbers and find the closed form expression? Okay. So we saw, we can use generating functions. We can use the characteristic polynomial. And when the dust settles, we get fn is 1 over root 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2 to the n. This is one of my favorite formulas in mathematics because this does not look like an integer, but is an integer. This number is less than 1 in absolute value. So this goes to 0 exponentially fast. This blows up. So really, the nth Fibonacci number is approximately 1 over root 5, 1 plus root 5 over 2 to the n. Right? How large is the square root of 5 approximately? 2 and change. 2 squared is 4. 2.5 squared is over 6. So it's somewhere between 2 and 2.5. So this difference is at most is going to be, the numerator is going to be less than 2. So in absolute value, this is going to go to 0. So what this means is the nth Fibonacci number, when n is large, is whatever integer is closest to this. Will this change the first digit? Is it possible that that changes the first digit? Can I just drop that if I only care about the first digit? What do you think? Could that ever change the first digit?
Probably not for a large n. Because if the second term goes to 0 really, really fast, then it shouldn't change like the leading coefficient. Or at least it's not like a number like 1,000, for example.
Ah, so what if this is really close to a number like 1,000? This could be 999999999.999999999, something like that, man. And then this just moves you up that small little bit. Or you could have, one zzz, lots of zeros, point zzz, lots of zeros, 1. And that moves you down just a little bit. So it is possible that this can change the leading digit. But it's going to be really tough, because the only way it's going to change the leading digit is if you are so close to one of these transition points. Now for Benford's law, you can look at more than just the first digit. You can look at the first 2 digits, first 3. You can look at the significand. And in the limit, the effect of this is going to be negligible. So there's really 2 steps here. The first step is let's study the simpler process where we take these pure numbers. So we'll call the sequence maybe, we'll call it AN will be 1 over root 5, the golden mean to the n. And I'll let Bn just be the golden mean to the n. We'll study these sequences first and show that they're Benford, or talk about what we would need to show that they're Benford and motivate doing more Fourier analysis or ergodic theory, depending on your preferences. And then we'll talk about how to deal with something like that. Okay? So the first thing is, we know something is Benford if and only if its logarithms mod 1 are equidistributed. So let's look at the logarithms. So let's look at the log of an. So the log, base 10 of an is the log base 10 of phi to the n plus the log base 10 of 1 over square root of 5. So it's n log base 10 of phi plus, or if you want to do minus 1/2 log base 10 of 5. But this is a fixed number. It has no independence. We only care about these values what? We don't care about the absolute magnitude of these numbers. What do we care about these numbers? When I'm looking at the logarithm, I don't care about the actual value. I only care about the value up to something. So when I'm trying to show something is Benford, you've got to know this stuff. The fundamental equivalence says a sequence is Benford if and only if the logarithm mod 1 is equidistributed. So I look at this mod 1. So when I look at this mod 1, if this is equidistributed mod 1, if I shift everything by a fixed amount, will it still be equidistributed? Yeah. So it reduces to studying this. The minus 1/2 log 5 base 10 doesn't really matter. It's just a shift. So enough to show that n log base 10 of phi is equidistributed mod 1. Or if you want, it's uniformly distributed mod 1. So the question is, when is the fractional parts of n times the number uniformly distributed? So what's nice is while we're studying the Fibonacci numbers, we're actually able to study things in a little bit more generality, so that we'll prove a result. It will immediately apply to Fibonacci's as well as others. So question. Fix an alpha. When is n alpha mod 1 equidistributed? So can anybody give me a choice of alpha such that n alpha mod 1 is not equidistributed? So give me an alpha where it will not be equidistributed. One alpha should be screaming at you. 0, right? Fails if alpha is 0. If alpha is 0, every number is 0. Okay, so it can't be equidistributed for all alpha. Is there anything other than 0 that causes failure for alpha? As soon as you know 0 doesn't work, you have infinitely many things that don't work. What else won't work if 0 doesn't work? Because we're only looking at things mod 1. So once you know 0 doesn't work, you know infinitely many other things don't work. Yes, but once you know 0 doesn't work, you shouldn't go to 1 over n. There's something you should go to before 1 over n. What is equivalent to 0 mod 1? Integers. 1, 2, 3, 4, -1, -2, -3, -4. If I change alpha by an integer, then I change n alpha by an integer. And since I'm taking things mod 1, there's no change. So it fails if alpha is an integer. Now the next thing was the suggestion to try 1 over n, or more generally any rational number. So let's say you took alpha to be 1/5. Then you would get 1/5, 2/5, 3/5, 4/5, and what's 5/5 mod 1? I'm sorry? It's 1 or 0. And then what would 6/5 be mod 1? 1/5. 7/5 would be 2/5. So if you take an integer, if you take a rational, it cycles. Fails if alpha is rational. We cycle. True if alpha is irrational. So all we need is alpha to be irrational. And if alpha is irrational, then n alpha mod 1 is equidistributed. And it turns out you can quantify rate. Rate depends on how irrational. So not all numbers are equally irrational. So I know there's at least one person here who is going deep in computer science. So when you do things in computer science, you work with zeros and ones. You work with binary typically. You try to approximate numbers using binary expansions. A really good question is, how well can I approximate a number with binary? Or how well can I approximate a number in any kind of system? And so when you're working with things on a computer, obviously, if I have a choice between two approximations and one is better than the other, do I want to use the better approximation? Can you give me a reason why I might not want to use the better approximation?
It's too
It's too expensive. Maybe it takes too much memory. Maybe it takes too much runtime. And so you have a trade-off. How much space do you have? How much processing time do you have? How much runtime do you have? And based on your constraints, you can then choose the various types of approximations. So we need to find good ways to approximate numbers. It turns out some numbers can be approximated by rationals better than others. And you can actually have comparisons as to which number is more irrational. And we'll say the worse rationals approximate you, the more irrational you are. So this is a class filled with seniors. You've got to be able to give me pi to a bunch of digits. I want digits of pi. Go. 2, 6. I'm sorry?
Yep, that's all I got.
And then I think the next one is a 5. All right.
2, 6, 5, 3, 5, 8, 9, 7.
Yep. That seems right. I remember the 5, 3, 5. Okay. So if you want to find approximations to pi, pi is approximately 3. Now, there was a place that actually passed a law saying pi equals 4. And I think I've told some of you what you should do if they declare pi to be 4. You buy land in square lots, and you sell it in circular lots. You do stuff like this. And if pi equals 4, what's the area I'm selling you? Yeah. No, I mean, if people don't know math, that's their fault. So here's an approximation. Can somebody give me a better, approximation of pi using rationals? I've got a decimal. Give me a good rational approximation, ratio of 2 integers. When I look at this, what do you see as your next approximation? Yeah, so I mean, we can do it slowly. 31 over 10, or 314 over 100, or 3141 over 1,000. Are these approximations getting better? Yes, they're getting better, but they're also expensive. The way I get an extra digit is I'm basically multiplying my denominator by 10. And so we measure the cost of an approximation by the size of the denominator. And a nice question becomes, if I want my denominator to be a given size, what's the best approximation? And so if I want my denominator to be at most 1,000, this is not the best approximation. As I think somebody had said 22/7. So if you calculate 22/7, this is the same as 21/7 plus 1/7. 21/7 is 3, so this is 3 and 1/7, which is 1/7 is about 0.1428, I think. Right, for 1/7. So using just 7, we get 3.1428. Using 10, we get 3.1. This is much better. So 22/7 is a better approximation than 31/10. And so we want to try to find good ways to approximate numbers. And we will declare that the better approximation we have, let me just make sure I do this right. The smaller the difference, the better approximation we have. It turns out that there is a number which wins as it has the worst approximation by rationals. Anybody know which is the hardest number to approximate by rationals? We have seen it today.
0.
No. Nope. Nope. Haven't seen that many more numbers. Has to be an irrational. I'm sorry?
Square root of 2.
Nope. Close to the square root of 5, though. So square root of...
Square root of 2.
Nope. Where are you seeing square root of 5?
The golden.
The golden mean. the golden mean is actually the hardest to approximate by rationals. You're going to have the largest error when you look at your good rational approximations. So the result is that if alpha is irrational, then n alpha mod 1 becomes equidistributed. A natural question to ask is, how quickly does it become equidistributed? If I look at 1,000 terms, how much do I expect to be off? And you can quantify that in terms of how well you can approximate the numbers by rationals. So we probably won't do too much on this, but I want you to be at least aware of this. And I want you to be aware of the fact that the golden mean is the hardest to approximate. If people find this interesting, I'm happy to give a lecture or two on this topic. But for now, we will lead up to a proof that if alpha is irrational and alpha mod 1 is equidistributed, but not say too much about how quickly the equidistribution sets in. Okay. So, theorem, alpha not in Q implies n alpha mod 1 is equidistributed. So for us, we need the log base 10 of the golden mean, which is the log base 10 of 1 plus root 5 over 2. We want to show that that's not rational. All right? Any thoughts as to how you would show it's not rational? So we want to show that the log of the golden mean is irrational. And then we can use that big theorem.
We can assume it's rational.
So let's assume it's rational. Assume the log base 10 of 1 plus root 5 over 2 is p over q. And we might as well assume that the fraction is in reduced terms. So what does it mean if the log base 10 of this is equal to p over q? It means 1 plus root 5 over 2 is 10 to the p over q. So I can cross multiply, and I get 1 plus root 5 to the qth power is 2 to the q 10 to the p. What kind of number is 2 to the q 10 to the p? I'm sorry? Rational. We can actually be a little bit stronger than rational. Rational is fine, but it's an integer. This is an integer. Is there any way all the root 5s could cancel? So what do we have here? We have the sum, n goes from 0 to q, q choose n, root 5 to the q, 1 to the n minus q. So whenever n is, I'm sorry, I'm doing n not q, sorry. It's root 5 to the n, 1 to the q minus n. Whenever n is an even number, then root 5 to the n is an even number. I'm sorry, root 5 to the n is a integer. Whenever n is odd, I have root 5 times an integer. So I can write this as an integer plus the square root of 5 times the sum. N goes from 0 to q. N is even. So I'll write n maybe as 2k. And then I'll have q choose 2k. And then root 5 to the 2k would be 5 to the k. What kind of number is this? So what kind of number is this now? Right. I need to be slightly more specific than integer. Positive. Yep. Non-zero would be fine. Positive is great. This is a positive integer. Since this is a positive integer, we know that there has to be a root 5 that's left. Is everybody comfortable with showing square root of 5 is irrational? Okay. So we would then get, when, integer plus root 5 times an integer equals an integer, we then get root 5 equals integer over integer. And that's a contradiction. So that proves that the square root of 5, the square root of 5 is irrational. It then propagates upward, and the golden mean is now known to be such that the log base 10 of the golden mean is irrational. Okay, so we can now prove almost that the Fibonaccis are Benford. So we know n alpha mod 1 is equidistributed if alpha is irrational, as the log base 10 of 1 plus root 5 over 2 is irrational. We deduce that n log base 10 of 1 plus root 5 over 2 is equidistributed mod 1. So this almost proves the Fibonaccis of Benford, right? Why don't we have the Fibonaccis of Benford? What's preventing us? So here's 0, here's 1. We have the sequences becoming equidistributed. That's great. We talked about how we have the minus, 1/2 log 5 base 10, but that just translates everything. So we could even put in the 1 over root 5 and we'll be okay. What's preventing us from deducing now that the Fibonaccis are Benford? So it's the term that's being subtracted, that thing that's exponentially small, right? We showed that this sequence is uniformly distributed. So in the limit, this sequence is Benford. Well, let's take digits d and d plus 1, not drawn to scale. Because the term is exponentially small, how could it change probabilities? Well, we could be really close to but below d plus 1, and it could add something and pull us forward. Or we could be a little bit past d plus 1, and it could be subtracted and pull us back down. And of course, we would have the same issue around d and d plus 1. So if we choose our n sufficiently large, as long as we're not too close to d or d plus 1, we'll be fine. Because we are uniformly distributed, the probability that we are very close to d or d plus 1 is going to be going to 0. We can make that as small as we want. And now we have to do some bookkeeping. Right? So how likely is it that we're going to have something that's going to shift us? We've got to be in this range and then have enough of a push to move it. So do you think it's likely or unlikely that we're going to have enough of a push? Yeah, so in fact, I've never checked, but it may be the case that for all sufficiently large n, there's never going to be a change in the first digit. Because you would need the golden mean to the end, or the 1 over root 5 golden mean to the end, to be so close to one of these critical values. So you give me any fixed epsilon, and the probability I'm in here Oh, this should not be d plus 1, I'm sorry. Since I'm doing things on 0, 1, this should be the log base 10 of d plus 1. And this should be the log base 10 of d, right? So the probability I'm in this region is converging to the length of that region. And then I just have to show, well, the probability I'm in this region and this region, I can make that arbitrarily small. So it's now down to just a bunch of bookkeeping. We've got about 4 minutes left, so I don't think I want to go through the bookkeeping now. I'll save that bookkeeping for Friday's class. And what I'll do, well, I'm hoping we don't have class on Friday. I think the weather report is pretty good. Yes?
Is there like a storm?
Oh, is it supposed to rain on Friday?
Yeah.
Oh, okay. I had heard it was good. Oh, okay. So then there is a chance that we will have class on Friday. Okay. All right. So I want to just quickly end. Friday's weather is raining? Ah. Next Friday I will be out of town, so why don't you just end briefly? Oh, that's annoying. All right, so continued fractions. So we can write any number x as a0 plus 1 over a1 plus 1 over a2 plus 1 over a3 plus dot dot dot. A0 can be any integer, and then all others are positive integers. And this is called the continued fraction expansion of a number. And basically, to denote it, we would often write x is a0, a1, a2, dot dot dot. And sometimes you put a semicolon here to just remind yourself that the first digit can be any integer and everything else. So the way you get approximations to numbers is you just truncate. And it turns out these give the best finite rational approximations to numbers. The continued fraction expansion is how you get good approximations. So the golden mean satisfies the relation phi squared is phi plus 1. This is coming from the recurrence relation, fn plus 1 equals fn plus fn minus 1. Guess fn is r to the n. And that'll give you r to the n plus 1 is r to the n plus r to the n minus 1. Pull out an r to the n minus 1, and you'll get r squared equals r plus 1. So we want to find the continued fraction expansion of phi. So phi is 1 plus root 5 over 2. What's the first digit in the continued fraction expansion of phi? I want to write it as an integer plus something that's less than 1. This is about 1.6. So this has to be 1 plus a remainder. So it'll then become root 5 minus 1 over 2. I add a half, I subtract a half. All right? So phi is 1 plus. Now let's multiply by root 5 plus 1 over root 5 plus 1. This is the old algebra technique from junior high of cleaning things. Root 5 minus 1 times root 5 plus 1 is just 4. So we would get 4 over 2, 1 plus root 5. One plus root 5 looks a lot like. So I want to put in a 2 here, so let's put in a 2 here. 2 times 2. Oh, 2 times 2 cancels the 4, so you get phi is 1 plus 1 over phi. So we now just substitute. Phi is 1 plus 1 over 1 plus 1 over phi. So if you keep iterating this, you'll actually see that the continued fraction expansion of phi is just all ones. And this is why phi is the worst approximable. The larger these digits are, when you truncate, the better approximations you get. And so one of the big issues is always how fast does behavior set in when the IRS is trying to decide should they audit. The big question is the deviation from Benford or one of the other tests they're doing, is it significant enough that malfeasance has happened, that foul play has happened? How quickly should you be converging to Benford's law? If you're off by this much, if you watched the video or went to Jay's talk, you would have seen that when we're looking at powers of 2, if you look at the first 30, you don't see any numbers that start with a 7. If you look at the first 60, I think there was one number that started with a 9. It takes a while for these things to set in. And that's why we want to do not just convergence, but we want to have an idea of rates of convergence. So today's lecture was to basically give you a sense of what's out there, how we attack these problems, and then to motivate the big proofs we're going to need to do. We're going to need to prove that if alpha is irrational, and alpha mod 1 is equidistributed. Okay, and that is, I think, chapter 12.